All right, in this video I'm going to be showing you about Jacobian change of variables, which for multivariable calculus is pretty much U substitution. All right, and I've got the rule right here, and I'll talk to you about that in a second, and I'll actually prove this rule in the next video. But in this video I'm just going to be computing examples and kind of reconciling with things we've seen already in this course. But the motivation is like, what if you had to integrate over this? I want you to think about that. This is a square. Okay, it's a square that's been rotated also. And you're like, oh, a square, I like integrating over, taking a double integral over a square. It's like, you know, just number. We like those. Okay, very simple. But if you think about what would actually go on if I tried to integrate over r in terms of x and y, I'd have to split this up into two separate integrals. Okay, I'd have to integrate, you know, kind of the left half of r as y ran from this curve to that curve and x went from 0 to 1. And then I would have to integrate on the right side of r between y between this curve and that curve, and x between 1 and 2. That would just be really annoying, right? Because I know that in some world this is like a very, very simple integral, right? It's integrating over a rectangular region. And really what we need to do is we want to just like rotate it, right? And we want to be able to just like treat this as a rectangle like it is. And so that is really what we're going to do. And if you think back to, if you took a linear algebra class, you think about, you know, rotations of things, linear transforms, that this is going to play it. And the effect of a linear transform on area, you may recall that's the determinant. Well, this area conversion factor is also a determinant. So this stuff is very interrelated. And I think maybe you'll see more about that in the next video. Okay. But so suppose I wanted to integrate axy with respect to x and y, over this region R. And I'm going to have a tough time doing that because, you know, these curves, well, this is regular. Okay, so what I'm going to do is I'm going to say, I need to kind of like parameterize these little curves. And I'll do that. I'll bring out some color. Just a second. All right. So maybe I'll say that this is these blue curves here. I've got, all right, this is y equals x plus 1. And this is y equals x minus 1. Okay, now these two curves, let's see, this is the point 1, 2, so this is y equals 3 minus x. Okay, yeah, 2, 1, yeah, got it. And then this is going to be y equals 1 minus x. Okay, and to just kind of save you a little bit of time here, I'm going to tell you that what you want to do is you kind of want to express these in standard form, okay? Just show you how it's going to end up happening. So the bottom curve here in red is going to be x plus y equals 1. And then over here, x plus y equals 3. Okay, and what I'm going to end up doing is I'm going to just say, I'm going to let u equal x plus y. And then I'm going to have u running from 1 to 3. And so in that sense, and you know, eventually maybe v will be something else, and it'll be rectangular in u and v, and that will be really nice. All right, so for my blue ones, I think what I'm going to do is I'm going to say x minus y equals -1 here. And over here, I'll have x minus y equals +1. Okay, so if I say that now I'm going to let u equal x plus y and v equal x minus y, I'm going to just have this region is something I can express as u in the closed interval 1 to 3 and v in the closed interval -1 to 1. Okay. And, you know, I think I might as well mention it here. I know I'm going to mention it in the next video for sure, but I need these conversions where I'm going from x's and y's to u's and v's. I need it to be invertible, because really what I'm doing is I'm taking u's and v's and I'm taking them to x's and y's, and you'll see how that works in the proof. So, it'll probably be nice and like linear, or y equals 1 over x, or y equals x squared, or something pretty invertible. But then they also need to be, in a sense, kind of parallel, if curves can be parallel, to make it, as nice as possible. Okay, there are other types of change of variables where this will still hold. That can just actually simplify the integrand and not necessarily the region, but I don't think we're going to do that in this course. If you're interested, you can talk to me about it. I can show you some other types of change variables because it's a very common technique in mathematics. All right, anyway, so I've got kind of my UV region set up. I think I need to get a formula for x and y in terms of u and v. That's kind of going to be the next thing, because I'm going to need this j in order to switch over to u's and v's. Okay? So what I've got a bunch of stuff going on here. Is that u equals x plus y, and I guess maybe I'll do that over here. And v is equal to x minus y. Okay, and maybe just for clarity, call that equation A and equation B. If I add equation A and equation B, I'll get that 2x is u plus v. So I'm going to get x is equal to half of u plus v. And then if I subtract equation A minus equation B, I'll have y minus a negative y is 2y is u minus v. So y is half of u minus v. Okay. Then, now I can take my partials and set up my Jacobian matrix. Okay, and that is what, that's why we call it J, is it's the determinant of this, which we would call the Jacobian matrix. Really, this transform from x's and y's to u's and v's is, it's a vector field. Okay, and we haven't really done those yet. So we haven't really talked about the matrix of first derivatives, matrix of second derivatives, what all that means, what we're going to use it for. That's kind of the next unit. But yeah, that's why we call it Jacobian, because this matrix is called the Jacobian matrix. All right, now, what was I doing? All right, I feel like it might be actually good for me to kind of draw in UV land. I don't need V is, yeah. And 1 to 3. All right, so, I'm just going in and drawing my new region, which, is kind of like R prime. R after a transform. And look, this is going to be a much nicer place to integrate than that. Okay. What else am I going to, okay, yeah, so I need to set up the Jacobian. So it's the determinant of dx du is going to be a half. Dx dv is also going to be a half. Dy du is a half, and dy dv is negative 1/2. Okay, this determinant is going to be, okay, negative quarter minus another quarter is negative half. And I do need to point out that over here we're taking the absolute value of this the determinant. I think I'll be able to maybe show you why that would be the case. Hold on. I'm gonna think about that for a second, and then maybe talk at the end of this example. I see it. I just want to be very careful about how I'm saying it out loud. Okay, so I think now I've got everything I need. I'm gonna just convert this into that's gonna be equal to the double integral over that of the r prime of 8 times x. I've got a formula for x and a formula for y. So, and maybe I'll just call this over r prime just for now. So I've got 8 times 1/2 u plus v times 1/2 u minus v times now absolute value of j dA. So that's going to be times a half dA now where dA is du and dv. Okay, this is kind of a lot to keep track of, so I'm going to just kind of clean this up. So I've got 8 divided by 2 is 4, divided by 2 is 2, divided by another 2 is 1. Okay, so this is now one double integral of u plus v times u minus v du dv. Okay, so that's going to be u squared minus v squared. I can go in either order I like because this is a rectangle in u and v. So what I'm going to do is I'm just going to say, hold on, just a second. Oh yeah, I'm just going to do du and then dv. So that's u going from 1 to 3 and v going from -1 to 1. Okay. Now, I suspect that this is the type of double integral that you should be pretty comfortable computing. So I don't think I'm going to carry this example the rest of the way out. It's just the setup. Okay, and just pointing out again that this half is positive because I take the absolute value of it. Okay. All right, now going a little forward on what's going on here. If you think about the length of these segments, well, you can see that, think about this triangle. This is 1, 1, that'll be the square root of 2. Here. And then same here. This is also going to be the square root of 2. So the area of this region is 2. Okay? And maybe I'll just say, area of that region is 2. The area of this region, okay, this has width. It doesn't look like it, but it is actually a square. I drew this very poorly. Made it look like a rectangle. But it has a width of 2 and a height of 2, meaning that this area is 4. Twice as much area. So what we're saying is that we need to account for the fact that we have twice as much area by dividing by 2. Okay, now it isn't always that simple when, say the Jacobian is not a constant, but it is it's kind of accounting for that. Okay, it's what are we dividing by? And that can have consequences in your integrand and stuff. But I think that this is a really nice, safe example of converting to, using v's to make something much easier. That's the whole idea here. We wouldn't want to do a Jacobian change variables, make an integral more difficult. Okay, this is hopefully going to just make it nice and easy, right? Something that otherwise wouldn't be. So I think that's a pretty good, safe catch-all example. Obviously, there's going to be ones that are a little more complicated than this. But I think I want to move on now and show you about the conversion factors for dA in polar and dV in spherical. I think that's what I want to wrap this video up with. All right, so let's talk about polar. We know that dA is r d theta. We know that this kind of conversion can really make integrals over round regions much simpler to compute. We've got some experience with it. I drew the pictures and showed you with geometry why this was the case. But let me just show you using the Jacobian change variables because it's really nice. What we need is a formula for x and y in terms of our other variables. Now our other variables are r and theta, but I think just to keep it as close to the statement of the theorem as possible, I'm going to go in and I'm just going to say, for now, I'm just calling ru and theta v, right? So u is r, v is theta. And then I'll go back and change it at the end. So, what are my formulas for x and y? X equals r cosine theta. So it'll be u cosine v. And y is r sine theta, so that'll be u times the sine of v. Okay, so we need partials of x with respect to u and v, and y with respect to u and v, and all that stuff. So I'm just going to start writing partials down. I'm going to say, all right, dx du is cosine v. Dx dv is equal to negative u sine v. Okay, dy du is going to be sine v. And dy dv is going to be, let's see, u cosine v. So this Jacobian, remember it's dA is equal to absolute value Jacobian times other dA. A prime. All right, anyway, so I'm going to take this, this determinant, and I'm going to have, let's see, oh yeah, set it up so I could just copy. Cosine V, sine V, negative u sine V, u cosine V. Okay, and then I can actually take that determinant. So I'll have u times cosine squared V minus negative u sine squared V. So it'd be plus u sine squared V. Okay, factor out the u's. I have cosine squared plus sine squared of V. It doesn't matter what V is, that's 1, right? So this is equal to just u. Okay. U is equal to R. So now I have dA as in dx dy is equal to absolute value of J, which is going to be the absolute value of R, which is pretty much just R. I'm going to just kind of gloss over that. And then dr d theta is the other A. I have not thought about that. Well, that's a real thinker. I have not thought about why we don't take the absolute value of R in this case. Might have to do with the nature of the polar substitution isn't going to like flip your region. One thing that you may have noticed, the reason that in the example I did earlier, the reason that determinant was negative was the upper section where it was like x plus y equaled 1 ended up being the lower section of the transformed rectangle, which meant that the thing had flipped over. Like if you were looking at the front side of the sheet of paper and then you transformed it, then you would be looking at the back. That's why that determinant was negative. I feel like maybe something about this polar change of variables is meaning that that won't happen. I have not ever thought about this, and if you have any sort of commentary you want to add to that, you can just add it below. But this is why, dA is equal to r dr d theta. Okay, I'm going to pause it, I'm going to go back, and I'm going to do it for spherical, but it is, it's a little annoying. And it's, it's one of those, it's a higher dimensional one. And so this stuff does work for higher dimensions, but we're just not going to do it in this class, because oftentimes the determinants are, too cumbersome to compute. All right, so this is our conversion factors for spherical, and I think that, actually writing out all of these partials is going to be kind of, writing them and then putting them in a matrix is going to be a lot. So I'm just going to kind of start with maybe the shell, and I'll start piecing stuff in. All right, J is going to be the determinant of a 3 by 3 matrix, which we know how to compute because we know how to take a cross product. Okay. First, it's going to be the partial of x with respect to rho, theta, and phi. It does not matter. You could do rho, phi, and then theta. I'm just going to do rho, theta, phi. Okay, so dx d rho is cosine theta sine phi. Okay. Dx d theta is going to be negative rho sine theta sine phi. And then dx d phi is going to be rho cosine theta cosine phi. All right, then on a y level, I might do this one a little quicker. So this is going to be sine theta sine phi. Okay, dy d theta is going to be rho cosine theta sine phi. And then over here, I'll get rho sine theta cosine phi. Okay. Then for z, this will be a little easier, I think. dz d rho is going to be cosine phi. dz d theta is 0, because I don't see any thetas in that formula. And this will be negative rho sine theta. All right. And then this determinant, this is going to be really annoying, except actually I'm going to choose this one as my, the one I'm going to expand on. So I'm just kind of pointing out I'm going to be using this one. And this is going to be equal to, and I need a new piece of white chalk. I've worn this one out. All right, so this is going to be equal to, all right, cosine of phi. Let's see, yeah. Cosine of phi times this kind of subdeterminant. I'm going to have a negative rho squared. Let's see, is there anything I can actually do here? Oh man, this is going to be rough. I'm going to say this is the type of thing, I'm going to just pause and work through it to keep this video. So the video is already getting a little long. I'm going to just work through it. I'm going to have a bunch of stuff here when it comes back, and you know, you can either work it yourself and check against me, or you can just believe me. All right, so this first one got rough enough that I had to abbreviate using S for sine. So sine squared theta, sine phi, cosine squared theta, sine phi, cosine phi. All right, what I'm going to do is I'm going to say that, right, I'm going to factor out the negatives. So I'll have it here, and I'll say that's plus. Factor out a rho squared. Okay, and too. I'll have sine squared plus cosine squared is 1, so those are going to be gone. Okay, this is very sketchy algebra here. But I've got 2 of these sine phi, cosine phi's. Okay, so what I have is in total, I have a negative rho squared times cosine squared phi times a sine of phi. And then minus rho, let's see if there's anything I can do with this. Oh, yeah, I can say I've got a minus rho squared here. I have a cosine squared plus sine squared, yeah, right here. So those are just basically going to be gone. So I can factor out the rho sine squared phi. Yeah, I feel good about that. This is rho squared sine cubed phi. Okay, yes, and this is what I'm supposed to get. Because if I factor out one of the powers of sine phi and the rho squared, I'll have, here it is, negative rho squared sine of phi times, what am I left with? I'm left with a cosine squared phi plus sine squared phi, which is a 1, okay? And, you know, if this is j, so dA is going to be the absolute value of j, d rho, d phi, d theta. And this is the conversion factor, right? Especially once I take the absolute value and I get rid of that negative. Okay, so this is where we get dV is equal to rho squared sine of phi d rho d phi d theta. Okay, that was kind of a lot. I'm not sure I'm glad I did it on the video. I can see I even went off the edge a little bit, but there's not much to see over there. Okay, this is Jacobian change of variables in action.